name's Arushi, and I'm a software engineer at Figma. Today, I'm going to be talking about how Figma enables real-time collaboration through our custom sync engines. So Figma has not one, but two sync engines. They're called Multiplayer and LiveGraph. For the last few years, we've grown a lot, so I'm going to be covering some of the scaling challenges we've had. And I specifically worked on LiveGraph, one of our two sync engines, so there's a couple of lessons about sync that we've learned along the way. But first, for those who don't know, Figma is a platform for teams to build products together. Our flagship product is for design, and it's designed to be fully online, so we have very limited support for offline capabilities. Collaboration is front and center because we believe the best products are built together, and we try to make that as effortless as possible for teams. So our design platform was the first design tool built for the web, and it set a new standard for building on the web. Our core innovation was multiplayer, like Jan said, and it was a big value add, and it showed that our bet really paid off. So multiplayer is inspired by conflict-free replicated data types. It's not a true CRDT in and of itself, because centralization is faster. I forget who said that earlier, but it allows us to have a faster and leaner implementation and also handle conflicts more easily, like when multiple clients are editing at the same time. Evan Wallace, one of the co-founders of Figma, has an excellent blog post on this, and I would definitely recommend it to anyone who wants to dive deeper into how Figma did this. However, Figma has other product services as well. So one example of this is comments. Comments appear in the canvas, but they're not built into the document type. They also appear in other product surfaces, such as the sidebar. We have surfaces like library publishing. So library publishing is one of the most powerful features in Figma, and it allows designers to make reusable components and styles in a library file, which then is queryable and consumable by other files. So a designer can make a button, and then you can go use that in all your Figma designs. So this type of data is derived from a file, but it's not pulled into other files through fetching that document itself. And then Figma as a product has many other services that are outside of the multiplayer canvas fully. So we have File Browser, for example. All of these surfaces still need to have real-time. So even in File Browser, we show active file users, anyone who's editing a file at the same time. So you could be asking, do you really need two sync engines? If we already had multiplayer, which syncs CRDT-like data, did we need to go build another one? Can we not kind of like format our data into this multiplayer model and reuse it? So there's a few reasons. Not everything can be a CRDT. So one example, active file users. This is kind of ephemeral state. It's state that lasts for the duration of a user session, and it would be wasteful to kind of persist that on the back end or build it into this document that's being synced with the server each time. There is also library publishing, which I said. So when a designer, for example, makes like a button in a library file that's then pushed out to other files, you don't really want them to be editing that button in the library and everyone who's using it to kind of see that data being updated in real time. Instead, we want the designer to be able to say, like, I'm publishing the button now, and then all the other files pull in that snapshot. So this is kind of like immutable derived state from the file document. And then there's also a lot of data that's fully driven by the server. One example is notifications, our notification bell. And these don't really fit into the CRDT model, and it doesn't really make sense to force that data into that state. But these features all still need to be live updating. So when we're thinking about this new sync engine we wanted to build for Figma, it was really about giving product engineers the ability to easily make the new features they're building live updating without any additional work on their part. So this was kind of our thesis around LiveGraph. Product engineers should be able to focus on feature development, not data sync, and especially not bespoke data sync for each of their use cases. So LiveGraphs look something like this. And I hope you're familiar because the Convex talk had a really similar API. But we have a use subscription React hook that automatically re-renders React components when the underlying data has been changed. And I just wanted to give one example of how multiplayer and LiveGraph kind of work together to keep Figma real time. So this example is thumbnails. In Figma, we show a thumbnail image of a file in the file browser. This image updates as the file is being edited, and you can set a thumbnail image as well. So what the model for thumbnail looks like is kind of like this. We have clients who are editing a file that goes through multiplayer, which is synced to our Fig file storage backend. LiveGraph is tailing database updates, getting updates on this thumbnail image, and this is kind of read back down to other clients that are looking at the file browser. Cool. So a quick recap, here's the differences between multiplayer and LiveGraph. Multiplayer syncs the raw Figma file data, while LiveGraph syncs data from non-file sources in the Figma backend. So Postgres and Redis are some examples. Multiplayer handles both reads and writes over a WebSocket session to our multiplayer server, while LiveGraph is a read-only system. So all writes go through our REST API legacy backend. We do have optimistic updates to give product engineers that ability to more easily surface over writes, but yeah, LiveGraph does not handle any writes. And then multiplayer, like I said, is inspired by conflict-free replicated data types, while LiveGraph is actually inspired by GraphQL, really kind of focused on this idea of ergonomics for product engineers, but with the key addition of live updates, because that was a must-have for us. Okay, cool. So yeah, I wanted to share a couple of lessons from scaling Sync at Figma. When I first joined, we supported a few use cases on LiveGraph. It was like comments and design systems. And we had, I think, like several 100,000 users every day at peak. Now that number is into the millions, and LiveGraph is a P0 critical service at Figma. So if LiveGraph goes down, the site is down. And this was like a huge shift from where we started. Okay, so not all sync engines are created equal. And I've really enjoyed this morning seeing like the variety of sync engines that we've gotten to learn about. But a lot of times when we talk about sync engines, we're looking at a model that looks like this. You have some data on the server, and you're trying to keep that exact data on the client in sync with each other. This is a model that we use for multiplayer. It's one Figma document that the client reads and the server persists, and we're trying to keep that in sync. But when we talk about LiveGraph, that's not the model we have. We have some data on the server that can be written to by a lot of clients, and we have a whole bunch of transforms happening in the middle. So what clients see is not what's persisted on the backend at all. So this caused a lot of pain for us in scaling LiveGraph, and this idea that you can like transform data and keep having it live was what some people say the original sin of LiveGraph. And it's because scaling multiplayer was relatively proportional to scaling. You scale up your servers at the same pace that we're growing the number of users on a Figma file. For LiveGraph, that was not the case at all, and our growth in traffic is actually really driven by us handling these computations, which can get really big, can do arbitrary business logic in them, and can potentially like refetch more data underneath. And this also poses a problem for us when it comes to thinking about correctness of sync. So for example, if you have a query that's maybe fetched in some view and some computation, and those are both watched by the same client, ideally, if that query gets an update, you show that change to the client at the same time in both like the normal data case and the computation. So for example, if you had like comments on the canvas and then comment count off to the side, that's really easy to do client side. But if you were going to put that in a computation, you want those things to always stay in sync. So with computations, it's hard to do this. They take time to run. You can go fetch off more data, and it's really hard to deliver strong consistency under this model. Cool. So beyond the architectural and kind of like use case differences with multiplayer and LiveGraph, we also had a lot of scaling constraints that were different. So multiplayer sync is limited to the file itself, while LiveGraph is like any data on the Figma backend and can allow arbitrary computations over that. And then multiplayer is also limited to 100 clients of the same file, while LiveGraph is very different. We have data on the backend. You can be read by any number of sessions. Cool, yeah. So in scaling LiveGraph, another lesson we learned is that things get complicated really easily. Okay, so back to this model. This is like kind of getting towards where we deal with things that we deal with in LiveGraph, but it's like not quite complete. In LiveGraph, we have many clients, so the model looks something like this. And thanks Figma designers for these lovely illustrations I didn't make. But this is still not complete because at our scale, you can't serve data directly from the database. You need to throw a cache in between it. So yeah, this is a difficult problem, and LiveGraph's architecture today looks something like this. We have our primary server with a query cache in it. It's building views over our GraphQL-like object graph. This also manages permissions and runs computed fields. And we tail the Postgres replication stream for updates. These updates then get propagated through the server down to the client over WebSocket, which maintains a local object store. So it's a stateful client. Yeah, so it actually looks really simple on the slide, but it a lot of times feels like we're trying to build our own database working on LiveGraph because we have an index for maintaining which queries are updated depending on like which database mutations. We have some form of transactions. So for example, upon a database update, we try to send all the query updates out in one batch. And we tail the replication stream just like actual database replicas. Which leads me to my third lesson, which is that scale directly informs design. Seems very obvious when I say it, but there's a couple of interesting examples of how this played out in LiveGraph's evolution. So when LiveGraph was first created, we were running all of Figma on a single Postgres instance. It was the biggest Postgres instance that Amazon RDS offered, but it was still one database, and it was constantly at risk of toppling over. So for this reason, we decided on an architecture that never requeries, basically, upon an update in LiveGraph. Instead, we send a minimal diff at each layer of LiveGraph to get to update the client state. That architecture looks something like this. So the database sends down row mutations that the query cache mutates its in-memory state from, sends out query mutations to our server, our main LiveGraph view building server, and we have an isomorphic client and server. So that allowed us to iterate really, really quickly because there was a lot of shared code between client and server. And it also allows the client to kind of process these similar minimal diffs that the server is processing. It's a very stateful and mutation-based architecture. So we have this stateful query cache, stateful server, and stateful client. And this is really hard to scale, as we've realized. For example, if you drop in the middle of a stream, say in the server, you can't be sure, like, is it safe to replay updates or not? A lot of times these mutations can't be reordered. There will be correctness issues if you reorder them. Yeah, so it's very, and when one of like a server goes down, you have to refill that whole state, which could cause a thundering hurt on the database. So very hard to scale. But yeah, this isn't the world that Figma lives in now. Today, we've sharded our databases both vertically and horizontally, and we have replicas for each primary instance. So we're slowly moving towards this world where we have a stateless and validation-based architecture. So the database can send query invalidations to our query cache, which sends view invalidations to our server view cache, and we rebuild in order to get the new state to send down to the client. This breaks the isomorphism between the server and client, but it allows us to have a stateful client and the data on the back end with a bunch of stateless layers in between, so we can really easily scale out the layer that we need to scale out. Cool. Okay, another interesting thing that's happened as we've scaled is this question that's coming up, like, do we even need LiveGraph? So as the number of Figma users has increased, the percent of traffic with live updating data has decreased. And even though the volume has increased, it's like the percent of data that's being sent down to the client as a result of other people's active changes, that's like what's gone down. And this is due to a few reasons. There's more Figma users, so more people who are not designers, and maybe they're just viewing a file. But also, LiveGraph was really built for this case of being ergonomic for product engineers to use. And because that happened, product engineers started using LiveGraph off the cuff for a lot of features they're developing, not necessarily those that actually need to be live updating product surfaces. So we've started to think about a lot of different problems that we weren't thinking about at all when I first joined, and one of those is initial load prioritization. So when I first joined Figma, the stage that LiveGraph was kind of at was like, can we consistently serve comments without LiveGraph server going down? Like I said, now Figma powers critical user flows such as the file browser. So it's a lot more important that in failure scenarios, we can serve something rather than like being able to serve updates all the time. So one of the ideas that we've kind of been thinking about in this space is initial load prioritization, where we do the initial view fetch over HTTP and then open a separate WebSocket subscription for updates. These two things do need to be like linearized and merged on the client, but it allows us to scale a lot easier because, for example, we have whale users, people who fetch like huge views at a time that can overload our server. With initial fetch over HTTP, you can spread that load out across many servers and allow the load on any server to be more predictable. It also gives us some other nice benefits in failure scenarios, such as graceful degradation. In the case of an incident, you can choose to just kill the updates and still be able to serve limited functionality on Figma. Yeah, and I thought that was an interesting example because it's really only something we've been talking about in like the last few months. This is not anything that we were thinking about like a couple of years ago. We were just trying to keep live updates working properly. So yeah, that's kind of the 3 lessons I have. I've had a lot of fun working on sync engines, and I think James maybe said this, like I love it and I hate it. That's kind of how I felt as well. But yeah, if you have any questions about more technical details, I know this is pretty high level, so feel free to find me afterwards. And thanks for listening. Thanks to my team.
Anybody? All right. Can you speak more about Thundering Herd? Like if that has actually happened and you guys have kind of killed the herds?
Yeah. This is actually in my presentation the first time and I took it out. But because we have so many stateful layers, when one thing goes down, you have to kind of refresh all of that state, which causes a lot of load on the database. So I'll pick an easy example. Our clients, when they reconnect over WebSocket, they try to get all of that data again. So every day when we deploy, all the clients disconnect and then they reconnect, try to get all of their state again. In the beginning, we actually didn't deal with this problem at all. We decided to just deploy very slowly. So it would take like 2 hours to deploy LiveGraph. But one of the ideas that we've been working with recently is to reconnect using a cursor. So that does require like global ordering of your update stream, but you can have a cursor that goes all the way down to the client, for example. The client can send up the cursor on reconnect, and then you only need to rebuild state that might have changed.
My question is 2 sync engines the right number of sync engines for Figma? Or should it be maybe a smaller number or a larger number? Or is that just what you kind of landed on in development?
Yeah, that's a good question. For a time we had, I don't want to say 3 sync engines, but we had like 2 sync engines and something that was trying to do something similar. Yeah, so multiplayer, it's all about like the specific use cases, I think, and multiplayer was like specifically for this canvas use case, and LiveGraph was very much for like the product engineering ergonomics and like let's not have anyone spend more time. I do think there's a lot of use cases that LiveGraph has that probably could be like a simple event stream that the client's hooked up to and then you refetch. But because we built LiveGraph in-house and it integrates with things like permissions, it's really nice to just have that, all of that like framework for free for product engineers. Yeah. Yeah, what do I think about integrating real-time text editing into Figma, like in the canvas? I do not work on multiplayer, so I'm gonna sidestep that question. Yeah.
Question, how do you guys handle bad connections? Like, do you guys fall back on something besides WebSockets, like long polling, or what is the general approach you guys use for this, particularly with like enterprise networks have these weird issues and whatnot?
Yeah, we considered doing HTTP long polling, but we only have WebSocket right now. So yeah, because the client is stateful, like you can, it doesn't fully break whenever the connection goes down. Like there's a couple things you can do, but yeah, we don't have any other backup.
Got it. And then so like for the new Figma Slides product, is that leveraging LiveGraph as well?
Sorry, I don't know where you are, so I don't know where to look, but it's again both multiplayer and LiveGraph. So the part of Slides that is like multiplayer collaboration on a canvas, like if you use in Slides, you can toggle between design and the Slides mode. Those are basically the same thing. It's the canvas, which is multiplayer. The things around it are a lot of LiveGraph.
Any other questions?
Hey, yeah, simple one. In which language did you implement the backend part that tails Postgres in?
Yeah, so multiplayer is implemented in Rust, and it used to be TypeScript. We moved to Rust. It's completely Rust now. LiveGraph is a mix of TypeScript and Golang. So originally it was written in TypeScript, and we're like slowly moving things over to Golang.
All right. Well, one more? Okay. What was the point? Wait. There we go. You're on my blind spot.
No worries. Hi. I know you talked about kind of how LiveGraph started being used by product like people in ways that you originally didn't expect. How did you kind of design the API in a way such that like people like use it for the right thing? And how do you think about that sort of like developer ergonomics and to kind of like lead them into the pit of success?
Yeah. So I feel like we were in a period of time where we were kind of just like, use LiveGraph, we're gonna support what you decide to use it for. We'll maybe build some stuff out for you. So for example, we have LiveGraph, like the schema language is kind of like GraphQL, but you can fetch from other backends, not just Postgres, like Redis, or you can fetch our REST API from it as well. And that made LiveGraph super powerful. It was kind of like self-serve. We've kind of shifted more into a zone of like, now we need product guardrails because it's a shared schema and shared schemas are really hard to maintain. So there's like a lot of over data fetching or like queries that we don't want to allow happening. So yeah, we're starting to add like guardrails around our schema, which a lot of like GraphQL open source is really helpful for like statically doing stuff on the front end.